Imagine a universe with absolutely no light. No stars, no galaxies, not even a single solitary photon to guide your way. Welcome to the Cosmic Dark Ages. A period starting roughly 380,000 years after the Big Bang. According to NASA's Cosmic Background Explorer data, the universe had finally cooled down to a balmy 3000 Kelvin. It was filled with a thick, suffocating fog of neutral hydrogen gas. A vast, endless ocean of invisible matter. If you were there, floating in the void, you wouldn't be able to see your own mechanical hands. Even if you brought the most powerful flashlight ever made, its beam would just be swallowed instantly by the hydrogen. So yeah, literally nothing to see here. For hundreds of millions of years, the universe was incredibly uneventful. But in the dark, something was silently working. Gravity. It never sleeps, and it's always pulling the cosmic strings. Invisible web-like structures of dark matter formed massive gravitational halos, dragging millions of solar masses of gas into tight clumps. These colossal gas clouds grew denser, heavier, and increasingly hot at their cores. The thermal pressure was building rapidly. The universe was basically a giant room filled with combustible gas, compressed to a tipping point, waiting for a cosmic spark. And then, the fog caught fire. The very first stars ignited, piercing the primordial darkness with blinding ultraviolet light. These weren't just normal stars. These were the legendary Population 3 stars, the first monster engines of the cosmos. They were alien, massive beyond our modern comprehension, and entirely devoid of the heavy metallic elements we see today. They were the brilliant, energetic pioneers that forever changed the fabric of reality. Let's see what made them tick. To understand why these first stars were such absolute units, we have to look at their cosmic recipe. And honestly, it was remarkably boring. 75% hydrogen, 25% helium, and a tiny, insignificant dash of lithium. That is it. Absolutely zero heavy metals. In astrophysics, anything heavier than helium is considered a metal. Our modern sun is sprinkled with carbon, oxygen, and iron. Why does this matter? Because metals act as cosmic coolants. They radiate heat away, allowing a massive gas cloud to fragment into smaller, normal-sized stars. But without any coolants, the primordial gas clouds of the Dark Ages retained all their heat. They aggressively resisted gravitational collapse. To overcome this extreme thermal pressure and force nuclear fusion to start, the gas clump had to be ridiculously huge. Gravity needed overwhelming numbers. So, when gravity finally won the arm wrestle, it didn't create a cute little yellow dwarf star. It birthed an absolute leviathan. Let's do a quick size comparison. Here's our beloved Sun, the mighty center of our solar system, holding all our planets together. And here is a Population 3 star. Next to this monster, our Sun is literally a rounding error. A microscopic speck of dust. Theoretical models and simulations suggest these ancient titans weighed anywhere from 100 to a staggering 1,000 times the mass of our Sun. They operated at the absolute extreme limit of astrophysics, right on the edge of what we call the Eddington limit. This is the critical tipping point where the outward pressure of the star's own blinding radiation is so intense, it almost pushes its own outer layers away. Because they were so massive, their gravity squeezed their cores relentlessly. This pushed their surface temperatures well beyond 100,000 Kelvin. At that insane temperature, they didn't just glow blue. They blasted the early universe with intense, highly energetic, and completely invisible ultraviolet radiation. These solitary, metal-free titans ruled the cosmos, clearing away the dark fog. But there's a cruel cosmic rule: the brighter the star, the shorter its lifespan. For a star, mass is basically its fuel tank. So, you would logically think that the biggest stars live the longest, right? Well, astrophysics is famously counterintuitive. Let's look at our Sun. It's a modest, reliable little engine that will burn for about 10 billion years. But a massive Population 3 star? It burns through its colossal fuel reserves in just 2 to 5 million years. A literal cosmic blink of an eye. Why the rush? Because gravity is incredibly greedy. The more mass a star has, the harder gravity crushes inward on its core. To keep from collapsing under that immense weight, the core has to fight back by fusing hydrogen into helium at a truly psychotic rate. Think of our Sun as a highly efficient hybrid compact car. It sips its fuel slowly and gets great cosmic mileage. A population 3 star is a monstrous, fuel-guzzling dragster with rocket boosters. It produces unimaginable power, but it empties its tank almost immediately. As the star furiously burns through its pure hydrogen, the core fills up with helium. Without hydrogen to burn, gravity squeezes even harder. The core temperature skyrockets to hundreds of millions of degrees, forcing the helium to fuse. And here is the magic moment. The star begins forging carbon and oxygen. The very first heavy elements, the first metals, are born in the dark. The star develops an onion-like structure. Heavy elements sink to the center, while lighter elements burn in the outer shells. Faster and faster. Eventually, the core of this hypergiant hits an absolutely terrifying temperature, over 1 billion degrees Kelvin. At this exact temperature, something bizarre happens. The high-energy light photons holding the star up suddenly turn into pairs of matter and antimatter. This is a fatal structural failure. The photons were the only thing providing outward pressure against gravity. And now, they are gone. With nothing to hold it up, a star the size of a solar system begins to gracefully, but unstoppably, fold in on itself. As gravity mercilessly crushes the star inward, it condenses the core to an impossible, suffocating density. The tension in the fabric of space is palpable. Suddenly, all that intensely compressed oxygen and carbon ignites simultaneously. It sparks a runaway thermonuclear reaction of epic proportions. This is not your standard stellar death. This is an astrophysical panic attack known as a Pair-Instability Supernova. Kaboom! The star erupts with an energy release so staggering, it completely defies human comprehension. We are talking about an energetic blast equivalent to billions of regular supernovas going off at the exact same time. For a brief, glorious moment, this single dying star outshines an entire galaxy made of 100 billion normal stars. Now usually, when a massive star dies, gravity wins the final round, leaving behind a dense neutron star or a terrifying black hole. We've all seen the textbook diagrams. The massive core collapses, punches a hole in spacetime, cue the dramatic dark abyss. But the Pair-Instability Supernova is the ultimate cosmic anomaly. The explosion is so intensely powerful, it reverses the collapse entirely. It completely blows the star apart. No black hole. No neutron star. Absolutely nothing is left behind but an expanding cloud of dust. The entire mass of the Titan, up to 1,000 times our Sun, is dispersed and scattered across the pristine cosmic void. And this total obliteration is exactly what the universe desperately needed. Remember those heavy elements forged deep in the core? Carbon, oxygen, silicon, and iron. They are now riding a majestic shockwave, traveling at a significant fraction of the speed of light. This wasn't just a violent explosion, it was a cosmic delivery system. The universe was getting its very first shipment of metals. The stifling dark ages were officially over, and the cosmos was now chemically equipped to start building something far more interesting. These newly forged metals, carbon, oxygen, and iron, completely changed the fundamental rules of cosmic engineering. Remember how the first hydrogen clouds couldn't cool down? Well, these heavy elements act as spectacular cosmic air conditioners. They absorb intense heat from the gas and rapidly radiate it away into space. This allowed the giant clouds to efficiently cool and shrink. Because of this cooling effect, gravity didn't need to form massive leviathans anymore. The clouds fragmented into smaller, more stable pieces. This led to the birth of the second generation of stars, known as Population 2. And yes, astronomers are famously terrible at naming things sequentially. population 2 stars were smaller, burned significantly cooler, and could live for billions of years instead of just a few million. Over billions of years, these stars also lived out their lives, slowly enriching the cosmos with even greater amounts of heavy elements. Fast forward about 9 billion years after the Big Bang, and the cosmic soup was finally rich enough for the ultimate recipe. A new kind of star emerged. A population 1 star, packed with heavy metals and complex chemistry. We call one of them the Sun. But the most crucial difference wasn't just the star itself. It was the dusty leftovers spinning in the disk around it. All that iron, silicon, and oxygen clumped together, forging solid, rocky worlds capable of holding liquid water. Without the massive energetic contribution of those solitary population 3 monsters, the universe would only be filled with gas giants. There would be no solid ground to stand on, no water to drink, and no carbon to form the complex basis of biology. Every single atom of iron in your blood, and the calcium in your bones, was literally forged in the blinding heart of a population 3 titan. But here is the million-dollar astrophysical question. If these first stars were so incredibly important, have we actually ever seen one? Finding a population 3 star is arguably the ultimate cosmic detective mission. You are looking for something that lived fast and died over 13 billion years ago. Luckily, telescopes are literal time machines. Because light has a universal speed limit, when you look deep into space, you are looking backward in time. But there is a massive problem. The universe is expanding, and it stretches the very fabric of space as it grows. As that ancient light travels for billions of years toward Earth, it gets stretched out along with space. We call this cosmological redshift. Remember how the first stars blasted intense ultraviolet light? By the time that light reaches us today, it has been stretched entirely out of the visible spectrum. To see the invisible dawn of time, humanity had to build the ultimate cosmic superhero, the James Webb Space Telescope. Those iconic 18-hexagonal mirrors aren't just for show. They are coated in real gold because gold is the absolute best material for reflecting infrared light. Equipped with JWST's specialized infrared vision, astronomers stared into what looked like completely empty patches of the night sky. And where Hubble saw nothing but darkness, Webb saw tiny, incredibly faint, deep red smudges glowing in the ancient dust. Through programs like JADES, the JWST Advanced Deep Extragalactic Survey, we found objects with a redshift factor greater than 10. In astrophysics terms, a redshift that high means we are looking at light that has traveled for over 13.5 billion years. We are literally seeing these primeval galaxies as they were just a few 100 million years after the Big Bang. The universe was still a toddler. But are the elusive population 3 stars hiding inside those red smudges? To prove it, we need to read their spectral barcode. Astronomers are desperately searching for a very specific signature, a massive spike of glowing helium, with absolutely zero traces of heavier metals. Recent data hints we might finally be catching glimpses of them. We are standing on the precipice of witnessing the literal first light of creation. So, we know their chemical recipe, and we are hunting their spectral ghosts. But what did a population 3 star actually look like up close? Because we've never photographed one directly, astrophysicists have to use complex theoretical models. So, let's fire up the imagination engine. If you look at our Sun, its surface is messy. It has dark sunspots, tangled magnetic fields, and chaotic, boiling solar flares. But a population 3 star had absolutely no metals to create that magnetic complexity. It is hypothesized they were eerily, perfectly smooth. Like flawless, brilliant sapphire spheres sitting completely alone in the endless, dark, suffocating fog of hydrogen gas. But they didn't just sit there. They fought back. They blasted out specialized, high-energy UV light called Lyman continuum photons. When these extreme photons hit a neutral hydrogen atom in the fog, they energetically separated its electron from its proton. This process, called ionization, effectively turned the opaque, blocking gas into crystal clear, transparent space. Around every population 3 star, a massive bubble of light and clarity grew. As more stars ignited, the universe started looking like a giant slice of cosmic Swiss cheese. This legendary phase is known as the Epoch of Reionization. It took hundreds of millions of years, but eventually, the bubbles completely merged. By about 1 billion years after the Big Bang, the fog was entirely gone. The universe was finally fully transparent, just like the one we see today. Now, as a fun thought experiment, what if one of these ancient, smooth, fuel-guzzling titans suddenly appeared in our modern Milky Way today? It would be an absolute spectacle. A single population 3 star would instantly outshine millions of neighboring stars. Its extreme ultraviolet radiation wouldn't just give you a sunburn. It would gracefully, but forcefully, evaporate the atmospheres of any planets within dozens of light years. So, while they were absolutely essential for creating the universe we live in today, we should probably be very glad they are all long gone. But jokes aside, the story of population 3 stars is the ultimate cosmic tragedy. It is a story of beautiful, absolute self-sacrifice. To build the complex universe, the simple one had to be completely dismantled. These pristine, ancient titans had to gracefully fade away. This began the grand tradition of galactic recycling. Every star that ignites today is built from the ashes of the ones that came before it. As the legendary Carl Sagan famously said, "We are made of star stuff." But now, you know exactly which stars he was talking about. You are the direct legacy of the most extreme, massive, and brawny engines of creation that ever existed in the history of time. As the James Webb Space Telescope continues to stare deep into the ancient dark, we might soon have the final, undeniable proof of their existence. Until then, the next time you look up at the night sky, don't just look at the bright stars. Look at the dark gaps between them. Because hidden in that ancient, stretched out darkness, is the brilliant, blazing dawn of absolutely everything. Whoa, that got deep. My cooling fans are spinning just thinking about it. Speaking of massive cosmic forces, have you engaged with the algorithm yet? If you enjoyed surviving the cosmic dark ages with me, hit that subscribe button. It generates enough gravitational pull to keep this channel alive. And drop a comment below. What mind-bending corner of the universe should we explore next? Black holes? Multiverses? The terrifying vastness of nothing? Don't forget to leave a like. It acts as a stellar coolant for my processors. You can also check out our other deep dives right here on screen. Alright, my cosmic data buffers are full. I'm heading back into the void to crunch more numbers. Stay curious, space travelers. And I will catch you in the next epic. Quanta-Bot out.